Have you ever stood around a campfire? The closer you get, the hotter it is, right? Step away, and it gets cooler. It's simple, intuitive physics. Now, what if I told you that our sun, the biggest bonfire in the solar system, does the exact opposite? What if stepping away from it made things not just a little hotter, but millions of degrees hotter? It sounds completely bonkers, like a glitch in the universe's code, but it's true. This is one of the most baffling and long-standing puzzles in astrophysics, a real head-scratcher, known as the coronal heating problem. Let's break this down. The visible surface of the sun, the part we see or shouldn't look at directly, is called the photosphere. It's incredibly hot, burning at a blistering 10,000 degrees Fahrenheit, or about 5,500 degrees Celsius. That's hot enough to vaporize just about anything you can imagine. But as you move away from this surface, out into the sun's wispy, ethereal outer atmosphere, the corona, something bizarre happens. The temperature doesn't drop, instead it skyrockets. The corona sizzles at an unbelievable 2 to 5 million degrees Fahrenheit. And in some places, it can reach tens of millions of degrees. That's hundreds of times hotter than the surface it's supposed to be heated by. Think about that again. The heat source is here, but the area far away from the heat source is astronomically hotter. It defies our fundamental understanding of thermodynamics. It's like your stovetop, being cool to the touch, while the air 10 feet above it is hot enough to melt steel. This isn't just a minor quirk. It's a colossal cosmic mystery that has had scientists scratching their heads for nearly a century. How on Earth, or rather, how on the sun is this possible? Where is all this extra energy coming from to superheat the corona? The sun must have a secret heating mechanism, an invisible furnace that's working overtime, and finding it is a holy grail for solar physicists. To truly appreciate this puzzle, we need to understand the sun a little better. It's not a solid ball of fire. It's a giant, churning sphere of superheated gas called plasma. This plasma is a chaotic soup of charged particles, protons and electrons all zipping around. And whenever you have moving charged particles, you get magnetic fields. The sun's magnetic fields are the key. They are immensely powerful and incredibly complex, twisting, stretching, and snapping like cosmic rubber bands. They bubble up from the sun's interior, creating features like sunspots, and extend far out into space, forming the intricate, beautiful loops and streamers we see in the corona during a total solar eclipse. Scientists are almost certain that this magnetic energy is the ultimate source of the corona's extreme heat. The magnetic field acts as a vast energy transport system, taking energy from the roiling turmoil deep inside the sun and somehow depositing it into the tenuous outer atmosphere. The billion-dollar question, though, is how does this magnetic energy convert into thermal energy, or heat, so efficiently and so dramatically? Over the decades, two main theories have emerged as the leading contenders, and the scientific community is in a heated debate over which one is the primary driver, or if it's a combination of both. The first big idea is a theory called nanoflares. It's a beautifully chaotic concept. Imagine the sun's surface as a tangled mess of magnetic field lines, like a giant bowl of spaghetti. As the plasma on the surface churns and boils, it constantly twists and braids these magnetic lines, building up immense tension and stress. Eventually, these lines get so tangled that they snap and reconnect with neighboring lines in a new, simpler configuration. This event, called magnetic reconnection, releases a sudden, explosive burst of energy. We see this on a grand scale, with solar flares, which are colossal explosions that can release the energy of millions of nuclear bombs. The nanoflare theory proposes that the corona is being heated by a constant, relentless storm of tiny, miniature versions of these flares. Each individual nanoflare is too small and quick for us to detect directly with our current telescopes, but there would be billions of them going off all over the sun, all the time. It would be like a perpetual, invisible firework display. Each pop, each snap, releases a little packet of energy that heats the surrounding plasma. Cumulatively, This constant peppering of energy from countless nanoflares could be enough to maintain the corona's multi-million-degree temperature. It's a compelling idea, heating the atmosphere through a death by 1,000 cuts, or rather, a life by 1,000,000,000 tiny explosions. The second leading theory is a bit more rhythmic. It involves waves. Not ocean waves, but a special kind of magnetic wave, called an Alfvén wave. These waves were first theorized by the Nobel laureate Hans Alfvén in the s. Think of a magnetic field line as a guitar string. If you pluck it at the bottom, near the sun's surface, you can send a wave traveling up its length. The churning convective motions on the photosphere are constantly plucking these magnetic field lines, sending these Alfvén waves rippling outwards into the corona at incredible speeds. For a long time, this was just a theory. But in recent years, thanks to advanced spacecraft like NASA's Parker Solar Probe and the Solar Orbiter, we've actually been able to directly observe these waves. We've seen them carrying a tremendous amount of energy up from the surface. So, the waves are there, and they have the energy. The remaining part of the puzzle is how that wave energy gets converted into heat. The waves travel through the corona, and as they do, they can interact with the plasma particles, shaking them and causing them to collide, which generates heat. This process is called dissipation. The theory is that as these waves travel further out, they begin to break or damp down, depositing their energy into the corona, much like ocean waves deposit their energy when they crash onto a beach. So, we have two fantastic culprits: the explosive, impulsive nanoflares, and the steady, rhythmic vibration of Alfvén waves. Which one is it? For a long time, scientists were in one camp or the other. It was Team Nanoflare versus Team Waves. But the truth is likely more complicated, and honestly more interesting. It's probably not an either-or situation. It's highly likely that both mechanisms are at play, contributing to the heating in different ways, in different regions of the corona, or at different times. For instance, nanoflares might be dominant in heating the dense, bright magnetic loops you see clustered around active regions on the sun. These are areas where the magnetic fields are strongest and most complex, making them ripe for explosive reconnection events. Meanwhile, Alfvén waves might be more responsible for heating the vast, open regions of the corona, like coronal holes, where the magnetic field lines stretch far out into the solar system, forming the fast solar wind. This is where modern solar science is so exciting. We're no longer just guessing from afar. We're sending probes to fly through the corona itself. NASA's Parker Solar Probe is on a daring mission, getting closer to the sun than any spacecraft in history, literally touching the corona. It's sampling the particles, measuring the magnetic fields, and feeling the heat firsthand. It's our messenger in the furnace, sending back unprecedented data that is helping us test these theories directly. We're finally getting the close-up look we need to distinguish the signatures of nanoflares from the ripples of Alfvén waves. Solving the coronal heating problem isn't just about satisfying our curiosity about a weird cosmic quirk. It has profound implications. The corona is the birthplace of the solar wind, a constant stream of charged particles that flows out from the sun and bathes the entire solar system, including Earth. The extreme temperature of the corona is what gives these particles the energy to escape the sun's gravity and travel across space. This solar wind shapes the magnetic environments of all the planets, including our own magnetosphere, which protects us from harmful cosmic radiation. Furthermore, the same mechanisms that heat the corona, magnetic reconnection and wave dissipation, are fundamental processes that happen all over the universe. We see their effects in the atmospheres of other stars, in the vast clouds of gas between galaxies, and around supermassive black holes. Understanding how it works on our sun, our very own cosmic laboratory, gives us a key to unlock mysteries on a galactic scale. So, that seemingly simple question, why is the sun's atmosphere hotter than its surface, is actually a gateway to understanding some of the most energetic and powerful processes in the cosmos. The sun is holding on to its secret tightly, but with each new piece of data, we're getting a little bit closer to solving the case of the missing heat. Thank you so much for joining me on this journey into the heart of a solar mystery. If you found this as fascinating as I do, please hit that like button and consider subscribing for more deep dives into the wonders of our universe. Let me know in the comments which theory you find more convincing, Team Nanoflare or Team Waves. Until next time, keep looking up.